Hello, everybody. My name is Gillian. Today I'm going to be talking to you a little bit about my research. So I'm investigating the resonance Raman enhancement in a two-dimensional magnet. This title sounds unfriendly, but I promise I'll walk you through it and tell you everything you need to know. I did my research in the Department of Chemistry with my advisor, Professor Ji Ling. So basically, I play with lasers. As you can see from the picture, I shine light on things, I see how it interacts with matter, and I see what I can learn from that. And so the crystal, or the system of interest, I previewed on the slide here, but I'll say more as we move on. So before we get too deeply into it, I just want to orient you to the field. So you've probably heard the words quantum or nanotechnology in your daily adventures. That's because we're living in the second quantum revolution. Researchers in the sciences around the world are all aiming to understand and exploit the quantum mechanical properties of matter to develop powerful new technologies, technologies that can store and transmit information with tremendous energy and resource savings. So one way that we store information is through a property called spin, which is intrinsically a quantum mechanical phenomenon. In simple terms, quantum mechanics dominates in systems that are really, really tiny. We're talking about atomic or molecular scale. So the system I'm looking at is a crystal called nickel phosphorus trisulfide, abbreviated nickel PS3. If we zoom in and look at the atomic level, we get this crystal structure, so we can see the atomic composition and the way that the atoms are all bonded together. And so what's really interesting and special about this material is that when we cool it down to very low temperatures, in this case below 152 Kelvin, which is minus 120 degrees Celsius, we see this emergence of long-range magnetic ordering of spins that arrange in a zigzag anti-parallel fashion. So the blue and the red basically represent oppositely aligned spins. And you can think of spins as just really tiny magnets that sit on the nickel atoms. So before I move on, this is what a typical sample of the nickel PS3 looks like that I would see under a microscope. The different colors represent different thicknesses. So that takes me to my two main research questions. The first is that it's still really difficult to sort of image or read out this magnetic order because we can't just look at it and see spin sitting on the atoms, unfortunately. And some of the existing techniques are kind of rare, expensive, limited numbers of facilities in the world. And so I guess the first is, can we develop a new technique to read out these spin patterns more easily that are more ubiquitous and accessible in most labs? And the second, which is more interesting, I think, is that there's a lot of physics going on behind the scenes in this material that still kind of needs to be untangled. So I guess the more scientific aspect of my research was that I was looking to elucidate the interplay of the magnetic and electronic and vibrational properties of this material. And I specifically used a vibrational technique, which I'll get into. But these elements are all talking to each other. And so we want to figure out how they're talking to each other. And then an application maybe far down the line, once we kind of get a better picture of these interactions, is maybe this can provide us with the insights to, in effect, design or even write spin patterns, which would be big news in the field of materials and quantum information science. So the technique I use is called Raman spectroscopy. The name doesn't matter, but basically I'm using light to shine it on a material, and I'm like sort of seeing the vibrations. And so this is the anatomy of the setup. It's not too complicated, but just as a brief overview, we have a laser. It shines out. It's guided through a pathway of different mirrors and gratings and is directed to a sample that we view under a microscope. The way the laser is aligned at the crosshairs is basically how I select what area I'm measuring. And then, so the light hits the sample vibrates and changes the light. And that changed light is then redirected through more gratings and mirrors, filtering out unwanted signal that takes us to a computer detector, providing us a readout that we can then analyze. So this is what the data looks like. This is called a spectrum. And in this form of spectroscopy, each peak represents a different vibrational mode. And this schematic on the right just kind of gives you an idea, like the arrows of how different atoms are moving with respect to each other. So as I mentioned previously, I'm interested in the interplay of electronic, vibrational, and magnetic properties. And one of the first experiments I did is called excitation dependence. So I go down the line, basically all the laser lines I have available. So lasers of different energies have different colors, and we shine them on the sample and record the same spectrum over and over, which is what we see in the center here. And you can kind of see just by looking at this that the different peaks or the different vibrational modes have different intensities depending on the incident laser we use. And to further sort of dig into this, what we can do is we can look at several peaks that I've labeled, like P1, P2, P3, and plot them as a function of the incident laser energy. And what we see is that there's this clear sort of maximum or enhancement around 2.2 electron volts, which is energy. And so that implies, or the takeaway is that there's this new 2.2 electron volt transition in the material that we are sort of able to indirectly see through this profile. So this was done at room temperature. What happens when we go below the magnetic phase transition temperature? We do the same experiment, but now it's cooled down to 80 degrees Kelvin, which is very, very cold. And we still see this 2.2 electron volt resonance, and we can't see just from looking, but if we do some math, we can see that the enhancement is actually larger, kind of on average threefold, but even more so for certain peaks. So that implies that the magnetic order in some ways facilitates this 2.2 electron volt transition. And furthermore, the peak I've labeled P2 exhibits the strongest enhancement at low temperature, which implies that the P2 vibration is coupled to the 2.2 electron volt transition. So we furthermore want to verify, is this P2 coupled to the 2.2 electron volts, and does it change with respect to the magnetic phase transition temperature? So we do temperature-dependent measurements using the 2.2 electron volt excitation. And if we plot P2 as a function of the temperature, we actually see this kind of clear inflection point just around the expected magnetic phase transition, around 152 Kelvin. This is anomalous in that this is the only peak that displays this behavior. So that suggests that this P2 is correlated to the magnetic phase transition. So I know that that was kind of a lot. But just to sort of summarize maybe the key pieces that I found is that I identified this new 2.2 electron volt transition in nickel PS3, which kind of gives us insight into how the P2 vibration and this electronic transition are correlated to each other. And furthermore, by the temperature-dependent measurements, we see this anomalous behavior of P2, which suggests that this vibration is coupled to the spin. And I propose that this 2.2 electron volt electronic transition is sort of the middleman that mediates the conversation between the vibration and the spin correlation. So again, I guess stepping back, we've identified these relationships between these different elements, sort of piecing together the complicated picture of this material, which provides, just more insight into what's going on. And so it's done. Okay. All right, I'm out of time, but thank you very much for your attention. I'd like to thank my mentors and my advisors. And yeah, I'm happy to take any questions.
Okay, we have 4 minutes for questions.
Great job, Gillian.
Thank you.
So I have first two curiosity-driven questions. One is not technical at all, but I'm just curious if you know anything about why the letter P is used for the index for the different features?
Yeah, that was notation that one paper used, but something I didn't mention is like phonons are kind of what we call the collective vibrations, and so I think it's like phonon 1, phonon 2. So I think that's the P.
And then, as you might guess, I'm curious where the unpaired spins are localized. It doesn't look like there are any close sulfur-sulfur contacts. Is that true? So there, in other words, sometimes there are structures with disulfides, but it doesn't look like there's anything of that nature here. Is that correct? Okay.
I'm wondering, why is nickel PS3 the substance that is used for this, and what are the applications of it in the future? Like, what is it used for that would make this so important?
Yeah, so it belongs to a class of materials. It's the anti-parallel spin alignment. So the name for that class of materials is called antiferromagnets, and there's many other different kinds. There's ones that share the same structure with this, and there's a few others, but I think that they're limited. There's a limited number that have been identified. And I think what we're maybe traditionally used to thinking about is ferromagnets, where spins are all like pointing in the same direction, so there's a net magnetic moment. But if there could be this, for example, like electrically induced switching of the direction, so the spins are aligned anti-parallel, but there's this crystalline axis that they're kind of pointing along. And all the animations kind of coming back to bite me. That they're kind of aligned along this one direction of the crystal. For example, if we could electrically induce this switch so that they were pointing along a different direction, that would kind of give you like the 0 and 1 that we maybe think of for like binary code. So we're trying to get ways to like physically encode two different, basically up and down maybe. But that's just one example. I mean, there's some other maybe more advanced things that are yet to be discovered. So it's very interesting from a fundamental perspective too, just to understand like what's going on in these many body interactions. Sorry, I don't mean to be like jumping around.
Hello, I have a couple questions.
Yeah.
The first one is, what was the biggest challenge that you faced when doing this experiment? And then what's your favorite part about doing this experiment?
I'd say biggest challenges are like, I didn't show everything I've done here, but oftentimes like making sense of what happens in a spectrum it can take a lot of time. You look to the literature and you kind of try to consult your intuition, but sometimes you see peaks or you see changes that just don't really make sense. And so I guess just trying to like make sense of the spectra and interpreting it can be really difficult. It's frustrating but rewarding. And I'd say that's one of the things I enjoy most about it is kind of cracking the puzzle. But in terms of physically doing the experiment, I kind of just enjoy the hands-on aspect of like tuning the mirrors and aligning the laser. Makes me feel like I can do things. I don't know. But yeah, I think I really like spin. I like magnets and I like spin. So yeah.
All right, we're all out of time for questions. Thank you very much, Gillian.